we're thinking about STAP, which is for n spatial dimensions, that is CL n, 1, 1. And there are two reasons that you might be interested in this. Well, the main reason you might be interested in this is because you want to do calculations involving space-time, because it's got this sort of time dimension here. Yes, and it allows you to do arbitrary hyperplanes in space-time. I'm going to talk a bit more about the geometry and its relevance to another task you might want to do, which is non-uniform scaling and camera transformations. I don't fully understand the connection here. Oh, and there's also this thing called Laguerre geometry. Laguerre geometry, and Leo Dorst has started doing a little bit of research on this, which is, and it's again, it's a thing that you could read about, that has been researched for a long time, actually. I think more than 100 years, but has maybe, well, fell out of fashion a long time ago. But there seems to be some people still doing interesting geometry with it. But anyway, yes, that's apparently the same algebra. And okay, maybe what I'm about to say is well known to some Laguerre geometry researchers. But okay, here we go. So the way that we're going to make things easy for ourselves is that we're going to have CL 2, 1, 1. So we're going to focus on 2 dimensions of space. So how do we visualize this? Well, 2 dimensions of space, fine. That just looks like you got stuff happening in there. But if you to understand what's going on with this algebra, which is quite large, you kind of need to think about 3-dimensional space. And you think of time going up. And the thing that we're going to do is we're going to choose an arbitrary plane within this 3-dimensional space. And it's going to be this plane, I guess. It's an arbitrary plane in 3-dimensional space, and the, in some sense, 2-dimensional plane that we're going to think about is going to be that plane. So there's stuff happening in there's geometric and / mathematical objects that you're going to think about, which are outside of the place that you can see, or the spatial dimensions that you can see. When you get to 3 dimensions, that's hard, but for 2 dimensions, it's not so hard, because you can picture 3 dimensions. There it is. All right, and first of all, what can you do in 2 dimensions? Well, you can have a rotation, let's say, and you can have a translation, and a translation is a rotation around a point at infinity. I assume you know all this stuff because that's projective geometric algebra. And in this picture, that would look like this. So you actually have a line that goes all the way through all of time. If you do a rotation around this line, then that gives you a rotation around the perceived point. And if you and as for a translation, well, a translation just means that you've got a point that's, let's say, just very, very far away. You got some point that's really far in that direction, and similarly here, if you had a line that was really far in that direction, you translate around that line, that gives you a translation in this plane. Okay, but there's another kind of transformation that's very important. Let me restart that. So I'm going to, here's our 2D plane again. Going to get very, very used to drawing these 2 pictures side by side. What you can, so those were 2 vertical lines. What if you had a horizontal line? Well, a horizontal line would potentially be invisible to a 2-dimensional creature, first of all. So let's say we've got this grey line here. So that's visible to a two-dimensional creature that's living in this two-dimensional world. However, if you drew a line, here, that is not going to be visible. Oh crap! But you can still do, in some sense, in the same way that a rotation is characterized by a rotation axis, this transformation can be the axis of a particular different kind of transformation. And if you're interested in the non-uniform scalings, then that's what I'm saying. We could use this. This could be a generator of a non-uniform scaling. But first, say, hang on. I've drawn one outside of that, or out of the orange plane. So, could a two-dimensional creature get some intuition for where it is? Actually, yes. So there's a thing going on with the algebra of space-time that's very different to the way that ordinary space works, and it is called. You don't exactly have rotations all the time. You sometimes have things called boosts. And a boost, what can it look like? So one place that if you look up a boost on the internet, you'll see something that looks like this. So you have let's say a grey point, and you have these sort of dotted lines, and that is something called a light cone. If you're in 1+1 dimensions, so 1 dimension of space, 1 dimension of time, and there's a transformation that the transformation can do something like this. It can kind of squeeze things. It goes like that, so sort of squeezing this way, but at the same time preserving that point there. Similarly, if you're in if you've got an extra spatial dimension. The equivalent of this picture is that you have something like this. All right, and I'm going to attempt to draw some particular planes, and so there will be these two red lines are important for how the transformation works, and those two red lines actually do cut our orange plane. It's very important. So it'll be something like this. And so if you perform a transformation with this grey line here as the axis, you will get a transformation which kind of pushes. For example, it could push toward. It could push like this way, right? Which will appear to somebody in the plane to be a transformation that kind of pushes away from the top red line and towards the bottom red line. But there's also this aspect of the transformation. There's arrows going up that way as well, and down this way as well. And those arrows will cause you to see a transformation kind of pushing away from the top line and kind of, towards the bottom line somehow. So this is a rather strange transformation to be thinking about, especially if you're in the two-dimensional context. I'm back again. So yes, you've got this. You've got a transformation that's kind of pushing away from the top red line and towards the bottom red line. And if you multiplied this grey line by -1, you can get the transformation that pulls away from the bottom red line and goes towards the top red line. One thing to say: so this pair of red lines is in some sense an object in your algebra. So kind of line pairs are a thing, and if you, for example, let's see, if you had two, let's say, blue points down here, well, what would they look like? Well, in the same way that this grey line kind of is connected to these two red planes that you can see, these 2 points can be end up being connected to something that's a bit like, well, yeah, it's a circle for each point, right? You kind of get, yeah, this effect. I can say more about why it's a circle for them, but one thing to point out is that if you connected these two, they would look like this. And if you connect these, if you were to take the join of these 2 points in space-time, if you were to take the join of the 2 points in space-time, you would get, they're enclosing 2 red lines. And if I've drawn 2 circles that are the same radius, so it's a bit boring. But if you, move one of those, let's have it be that this one is actually like close to the surface. All right, so it's like here, which means that the circle is going to be relatively small, like that. So it's going to look like this. And with this, if you connect them with a grey line, you get a pair of red lines which are actually intersecting each other. And again, the rule is that the grey line kind of implicitly, the grey line is implicitly, it's got like tendrils, and these tendrils are the red planes. And the red planes are always at 45 degrees. They're always at 45 degrees, sort of in this 3-dimensional space. They're always like diagonal planes. For any grey line, so long as the grey line is not at 45 degrees to the it's or basically a horizontal line, or it's close to being a horizontal line, there will always be a pair of those red planes which are at 45 degrees in the space that go there. Yeah, and so, what's kind of interesting, let's say this is point A and this is point B, and in STAP you can do A join B, and you can get, C equals A join B. And so you can kind of, if you've got these 2 circles in 2-dimensional space, you can get their, I think it's called their envelope, or it's one kind of envelope at least. Might as well call it an envelope. And so you can get those 2 tangent lines, which, is that useful? Hey, maybe. One thing that, possibly a bit more useful is, oh crap, I've made a serious boo-boo there, but anyway, just to briefly go to 3 dimensions, if you had 2 spheres in 3-dimensional space and you wanted their enclosing cone, it turns out that cone would be also their regressive product. And by the way, it's a sort of double cone. Or if you had 2 equal radius spheres, you could get their enclosing sort of cylinder. I want it to be in red because in all cases the spheres, in any number of dimensions, the spheres would be, we call them pseudo-vectors, because they are, okay, what's their exact grade? Well, Here they are grade 3. In 2D STAP, points / points, i.e. circles, are grade 3. If you're thinking about 3-dimensional STAP, then these spheres are grade 4. Yeah, so you can take the regressive product of two grade 4 objects and get a grade 3 object, which is the cylinder. Here, you're taking the regressive product of grade 3 objects, you get a grade 2 object, which is the line, and the line implicitly has that pair of red lines in the visible space, in the 2D space. You can. It sometimes helps me to, if I draw the 2-dimensional space and I draw these two red lines, or I draw a 3-dimensional space and I draw this cylinder, it sometimes helps me to say to myself, well, it's kind of like there is actually a grey line here that's kind of equidistant to the two. Like there's a grey line in there. That's a little bit of a distortion, because that's a kind of basis dependent thing. And in any case, again, when you perform the transformation that's characterized by this object, the points in the space are going to move, straight past this grey line that you've drawn in here. And by the way, you don't get this red cylinder doesn't have a similar. Well, it's got a transformation or associated with it, or a set of transformations, but it's not like the transformation you see here. Instead, in the equivalent in 3-dimensional space would be a plane pair. Well, I said that the cylinder is equivalent. In 3 dimensions, the things that are, would you say that a line in 2-dimensional space is equivalent to a plane in 3-dimensional space? Because you can reflect past a line in 2-dimensional space, you reflect past a plane in 3-dimensional space. Or would you say that a line in 2-dimensional space is equivalent to a line in 3-dimensional space? 3-dimensional space, you can rotate around a line, but in 2-dimensional space, you can't rotate around a line. You rotate around points in 2-dimensional space. So is the point more like the 3-dimensional line? Blah, blah, blah. You've just got to stay on top of it. Sometimes, yeah, you've got to stay on top of which things are equivalent when you increase or decrease the number of dimensions. But just to be clear, yeah, there are plane pairs in the 3-dimensional picture. And these plane pairs get the same sort of transformation that pulls you away from one plane and towards the other. And reminder that this cylinder here is grey. Oh, do you know what? Maybe let's do it in grey. Seem to have established that convention. No, wait. It's not exactly. It's not the same grade. You see, it's a problem for me as well. All right, just in black. The cylinder is grade 3. Yeah, grade 3. This plane pair is grade 2. And because it's in grade 2, it can be part of a handedness preserving transformation. And then this one over here is grade 2, to remind. Okay. And yeah, if you've got three spheres, right, which are equal radius, then the well, if you take let's call them A, B, C, and you already know that the regressive product of A and B, so A join B, A like that V, A V B, that's going to be this. So I guess I need another color for it. No, I'll try and draw it in red. Maybe if we draw it big enough. So red is being inconsistently. It's not consistent across the grades for the diagram I've just been drawing. So that there is A join C, and then this plane pair is A join B join C, or A join C join B. You know, there might be a sign change there, which is to say that you'll kind of go from this plane to that plane instead of that plane to this plane. But yeah, blah blah blah. All right, so those are quite useful geometric objects, and if you incidentally, if you're thinking about conformal space-time algebra, it's got this, and then it also allows you to curve these things. So instead of having just a cylinder, you can have, for example, a donut. You can have like a kind of a donut that's like tighter in one part than another. Then you've got these things. Okay, they're called Dupin cyclides, and there's other strange shapes that you can look up. But we're not going to talk about those. We're going to talk about space-time algebra projectivized. So we've got all of those, and I guess one other thing that's helpful to say is that I've drawn a sharp distinction between. I drew you kind of this earlier on, and I said that's a rotation, and this is a boost. And that corresponds to a horizontal line versus a vertical line. But of course, you can interpolate between the two of these. You can have a transformation that is somehow something in between a rotation and this weird sort of damn it. Wish I could get rid of that. No, I really can't. And this sort of transformation. And I don't have a full understanding of those in my head yet, especially because if you look directly in between them, you will actually get a third kind of transformation, which looks something like this. You kind of have a let's do it in yellow. So it's a perfect diagonal line. And that yellow line, it'll look like a point for our orange planar space, right? So there's the got that, and then this yellow line somehow has it's got one of these it's got exactly one of these sort of diagonal planes. That's a diagonal plane. It goes down like that. Sorry, this stuff is like confusing as hell. But like I say, I've got to push this idea out there. Otherwise, I risk forgetting it. So these are incidentally possibly involved in polarization. That's something that I've been thinking about with Moab, so slackline on the Discord. But yeah, it's a strange sort of transformation. It's something like if you apply this transformation, then the points will do stuff like this. Something like this. So, for example, this line would be sent to this line, approximately. But that point there would be preserved. There's our orange plane as usual. Oh yeah, here's, let's say that you see a point, and I'm not going to color it in, I'm just going to have it be a black point. We've got a black point over there, and it looks like this. And you might say, hey, if I've just got a point, how do I know what kind of point it is? That's a good question. This way of this geometry is annoying in that respect. Conformal geometric algebra has the same problem. Yeah, if you see a geometric object, if you see a point, you don't necessarily know what kind of point it is. What's its grade? What kind of transformation is it going to be involved in? You don't know the answers to those questions if you just have a point. Once you know what kind of thing it is, you could draw it. Let's say that it was you determined somehow that it was involved. It was involved in it does an ordinary rotation. You could draw a little rotation arrow on it. That's kind of your orientation markup, I call that. Or maybe you discover that it's the kind of thing that we saw earlier that we were just looking at with the weird single plane. So it looks like this, and you've got it's got that red line going through it, and you have something like, and so you could draw orientation markup that looks like that. Maybe you could do that. Oh, by the way, with those transformations, the red line is always preserved. It stays in place. Yeah, I don't know what's going on with those. That's a rabbit hole. But okay. Back to this situation. You're not exactly sure yet. You don't even know what grade it is, because it could be that you had one of these circles, and it was like connected to this kind of blue point down here, but then that blue point went up and up and up, and so that circle shrank and shrank and shrank, and until the blue point was like in the plane, and it would, I guess, have in some sense a little light blue halo around it, but you don't know that. This point could be that kind of thing, and this thing is grade 3, because it's the intersection of 3 hyperplanes in space-time, whereas this thing would be grade 2, because it's the intersection of 2 hyperplanes in space-time, or rather it's a reflection in one hyperplane in space-time followed by a reflection in another hyperplane in space-time. If you're thinking about the transformation that's involved in, oh god, I've done it again. What the hell is that? I don't know. But okay, so you've got those 2 different kinds of object. Yeah, it just is what it is. If suppose that you had, oh my god, what are these? Yeah, it's gotten really buggy. I need to maybe find a different whiteboard program, but the thing is that this pen doesn't work with many others. So suppose that you had, here's just a helpful little tool I figured out. If you had a line that was like this, let's say it's one of these gray lines, so it looks like this, and let's say that you don't want the gray sort of line. You don't want to be performing you don't want it to be associated with like these 2 red planes. You just want a point there, and that's it. And in fact, you don't just want a point there because that's ambiguous. What you want is to rotate around a point there. You want it to be one of these more greeny type points. Well, you can get that. So it's a simple formula. So let's say it's P wedge this thing that I'm going to call so it's this plane here, which let's just call it big P. Wedge big P divided by big P. Although possibly, I think you can just multiply by the reverse. Green P and grey P are in the same place, but they do different transformations. Green P does a simpler transformation, let's say. All right, so we were interested in non-uniform scaling, and now it's time. It really is time for me to get around to that. So I think there's also camera transformations to be found in here, but yeah. Anyway, so let's say that you've got a gray line, so it's a bivector again, and it's a gray line that's in the plane itself. So you actually get to see the thing. And like I said, these gray lines, they've always got those red planes. They're always sort of there. But in the case of this one, well, we've got the gray line. I guess you could say the red planes are maybe like they're zero thickness sandwiching the gray line. But yeah, so they're like that. Here's the thing, and this is, I guess, a pretty complicated approach to non-uniform scaling, but I think it may have some advantages. So let's say that you had a bunch of green rotation points like that. Okay, so this would be like this. If you do one of these boosts I was telling you about, one of these transformations that's like this, that will cause all of these green points to move towards the gray line. And I even made a little animation showing this a while ago. Here we go. So this is the transformation that I've just described. So yeah, you can do it. You can squeeze them towards there. Now, there's a bit of a problem here, which is that once you do that, so you start out with this green point. It gets moved to somewhere slightly closer. Let's now have it as a slightly different color point. There's the original green point. There is the moved point. Oh, or not. All right, I'll do it with this one. It goes to here. Well, this instead of being a perfect vertical line, it'll now be a line that's like that, which you don't get to see. It'll still be close to vertical. It'll be closer than 45 degrees to the vertical. It's impossible for it to get to 45 degrees to the vertical, but yeah, it will be different. And you can use it's called the rejection formula. Again, that's sort of like P wedge, wedge big P multiplied by big P reverse, and that'll give you like a vertical version of that thing there. So if this is P. So you got to stay on top of that, but it is there. The a thing that's let me say this is complicated. This is no good, right? This is not ideal that this is so complicated. I mean, especially because a non-uniform scaling, hey, I mean, in some sense you can just do that by multiplying it by a scalar. Multiplying your x coordinate by a scalar. That'd give you a non-uniform scaling that preserves the x-plane. But a nice thing about this setup is that there's two potential advantages, and they're the same advantages that you get with any geometric algebra approach. Advantages, like the drawback, is this horrible complexity, and possibly, I don't know, might not be computationally great, but number one, can reason about invariance. I can say what that means in a second, but the other advantage, let me just say it, is can interpolate nicely, I think. If you interpolate two matrices, you often get things that you don't want. And if you interpolate two matrices that have rotation components and non-uniform scale components, it seems plausible to me that it'll interpolate in a way that you wouldn't exactly want. I think the invariance thing will give us insight into that. But just to be clear, the dual quaternions are used by Crytek and Disney because they interpolate very nicely. Yeah, and okay, to be fair, if you want to interpolate using rotation, translation, and non-uniform scale, well, that's a 12 by 3 matrix, and in some sense the thing that you're trying to get rid of by using the dual quaternions is now welcomed in the non-uniform scale context, because a shear mapping, which is what you get if you interpolate two matrices, is a non-uniform scale. But so let me say the thing about invariance. If you want, let's say that you've got a two-dimensional shape. So you've got some smiley face, and you actually want not that smiley face, but this smiley face. All right, so you want to squeeze your big smiley face to get your smaller smiley face. What is the what's the invariant, the geometric invariant? Well, it's easy. We can eyeball it. We can say, hey, do you know what? There's a red line. Well, not exactly, because I didn't draw the face perfectly. Let's draw it better. All right, we're scaling towards that red line. And that red line is, I'm not necessarily saying that it's one of those red planes, by the way, but that red line is something that we might maybe want to reason about. So if you're a 3D artist and you want to do a squeeze at a certain, you want to do a very specific squeeze. You don't just want to squeeze around the origin, all right? We want to do things away from the origin, just like how dual quaternions allow you to do things do rotations away from the origin. If you want that red line, or in three-dimensional space it would be a red plane that you'd be squeezing towards, then you get that object as a blade, a blade being, a wedge product of grade 1 elements. You get that. It's a specific array of floats that you could make and reason about. Yes, of course, you can do that with an ordinary plane as well, but it might be more complicated to do it with an ordinary plane. When I say an ordinary plane, I mean like ABCD, or XYZ distance, right? That's how we often represent planes. You want to be able to do a squeezing towards a plane. Maybe you even want to do something like a squeezing towards a plane followed by a rotation around a line that's perpendicular to the plane. That sounds a bit more obscure, but the thing that artists do is that they kind of layer these transformations on top of each other, and we'd like to be able to keep track of, as programmers, we'd like to be able to keep track of which ones they have, about what the geometric invariant is of the potentially very complicated transformation that they've made. They've translated it, they've rotated it, and they've scaled it, but they've scaled it in this, not in X or in Y or in Z, but some other plane. Again, layering all those up, you have some geometric invariance, and those geometric invariants will be elements of your transformation. So you'll have again, the algebra is CL3. If you're in 3-dimensional, for the sake of argument, we're thinking about 3-1-1, so quite a complicated algebra there. And so if you think about an arbitrary handedness preserving transformation, for the sake of argument, that'll be might as well draw it out. So it'll be one. There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 floats, and that gives you an arbitrary translation, rotation, non-uniform scaling, potentially camera transformation as well. And that sounds pretty familiar. That sounds like a matrix. This thing isn't a matrix, to be clear. Oh no, it's some matrix, but this is not. This wouldn't directly map to a matrix. Yeah, you could have a more minimal representation of it if you wanted to. You could use, instead of representing the whole thing, you could just have the bivectors, and you could exponentiate it when you want to get your transformation. In fact, the exponentiation is how you do your nice interpolation. So I guess that is more or less it. Yeah, because just to connect these two, where in order to get your nice animation, your nice interpolation, you will be taking the logarithm of a rotor, blending the bivectors, so adding them together with some weights, and then exponentiating back again, and at every point in that, you can say, hey, what are the bivectors? What's the bivector part of this object, which might just be a bivector on its own? And you can visualize the bivector, and potentially, debug it a bit better. Oh, I guess it's also worthwhile to say there's this whole thing called Lie sphere geometry, which asks the question, if you've got 3 spheres, can you find their common sphere that's tangent to them? And it turns out there's quite a lot of answers to this question. Those are the only 2 I can think of right now, but there are 8 answers, and you get a better you get a way of conceptualizing that question, we're maybe not so interested in it, but it was a big deal, and it led to lots of maths in the 1870s. That was Sophus Lee's PhD dissertation, and Lie as in Lie algebra and Lie group. Yeah, you can get these tangent things, and you can get them because that, again, we've got this going on, and our circles are actually looking like that, and they actually have like points beneath them. This one's a little bit further, and this one's very far, and this set of points can be reasoned about. Well, helps you get this solution. I'm not exactly sure how, but yeah. You also get, in comparison with conformal people say that if you want to do spheres or circles in geometric algebra, you should use conformal geometric algebra. That is really not obvious to me. Obviously, so conformal geometric algebra, it certainly does have spheres and circles, but they are a nonlinear representation, which is very bad. They make some things more complicated than they need to be. So you can ask, like, okay, let's say I'm in conformal geometric algebra, and I've got this circle and I've got this circle, right? And they're even concentric to one another. What's the difference in the coefficients between the two of them going to be? Surely something's going to change linearly. Answer, no. Whereas with this thing, you do get a linear representation. Just quite simply, a larger sphere means that the dark blue point has been moved downwards, or upwards, by the way. That would require maybe a different colored circle, because these blue points have a cone going up and they have a cone going down. It's the null cone in some sense, but it is the null cone. Yeah, so that's a linear representation. And in terms of transformations, by the way, you might want to have a reflection. Let's say you wanted a reflection in this line, followed by. Why would you want this? You might want this if you were doing space-time stuff, but it might turn up in our non-uniform transformations thing as well. Let's say you wanted a reflection in that line, followed by one of those transformations that takes you from this line to this line. Well, that would be in the larger view, that would look like this reflection plane here added to that a blue point down there. Yeah, and this, you kind of implicitly get the blue point sort of circle like that. Yeah. And I should have drawn these lines in red, because they're the kind of implicit lines associated with that. The line that is the grey line that is sticking out of that point and is orthogonal to that plane. That's how these transformations kind of compose, and that's why I say that these blue points kind of have that light blue circle, because a blue point, you can imagine the set of all diagonal red planes that pass through it, right? It's quite hard to draw that, but you can imagine it, and that the totality of those is this sort of circle. All right, stop it there.